All right, cool. Take two. So, welcome back to my kitchen. You can see in the background there's an oven there. Oh wow, my camera actually tracks my movement. That's new. So yeah, you can see my extremely professional setup. Here I am in my kitchen, but I know you guys aren't here for the professionalism. You're here for the physics. So last time, I constructed the theory of fluid mechanics for you very, very carefully with all the assumptions laid bare. And the reason I did that is because I think it's actually kind of important that we realize where physical theories come from. That is, a lot of times physics seems like magic. We just kind of have these equations, and they sort of describe this system. You have to realize that the equations are math, and the system is nature. So it's not expected at all that the math would describe a real physical system in nature. That's kind of the interesting part. So that's why I went through exactly what these mathematical constructions are. That is, like in Newtonian physics, we assume a point mass, and that's an idealized mathematical object, and we use it to try to predict a real object in nature. So that's why in fluid mechanics, I went over the parceling and the coarse graining and what these fields actually mean and everything. That's why I think that's really, really crucial. So with that understanding in our arsenal, I'm going to go through the intro that Tong wrote here in his notes. It's a really nice intro. It's actually quite beautiful, and it talks about the universality of the laws of fluid mechanics. And you'll see this a lot in physics. And it's another reason why I did that construction very carefully and rigorously last time. Is that you notice when I kind of went through the process of building up the theory of fluid mechanics mathematically, I assumed a couple of things, but I was agnostic towards a lot of other details. I didn't say the fluid was water. I didn't say the fluid was air. I didn't even say the fluid was matter. I said the fluid was just a bunch of stuff, and it just kind of behaves in this way. So that's why he talks about the fact that it can describe gluons, it can describe black holes, it can describe a lot of different things in nature because we are agnostic toward those sorts of details. We were just talking about fluid in the most general sense. And the things that we do actually assume that do actually form constraints are just conservation laws. And we see this a lot in physics. The conservation laws are very, very fundamental. So we don't assume that the fluid is any particular kind of fluid. All we assume essentially implicitly in the math is that mass is conserved, energy is conserved, momentum is conserved. Those are the things that are kind of the are going to form the equations when we make them. When we ultimately make the Euler equation and we make the Navier-Stokes equation, the reason that those equations hold and what those equations are really saying is that those things have to be conserved. That's kind of what they're saying. So we're not saying that anything about the details of the fluid, just that these kind of things are conserved. And that doesn't have to work. We could have done that and it could have just not described nature well, and then we'd have to go back to the drawing board. So this really isn't magic. A lot of times with physics, you're just kind of theorizing, and then the experiments show you're right or you're not right. Obviously, that's the scientific method. So yes, a lot of physicists are really geniuses, but we're not gods. We're sometimes we get it wrong, and you only see the right answers basically when the theory does work. But through many, many years of making these theories and the history of science and standing on the shoulders of giants, we get theorists that have very, very good intuitions for ultimately what theories are going to work. So with that, I told you that we have this field, and it's just like X and Y, let's say. You can have a Z too if it makes you happy. But basically, every single point in this field, these coordinates, every point in space will have two fields associated to it. Rho, the density field, and then U, the velocity field. Density field is pretty simple to understand or like conceptualize of. It's basically just like at every point in this fluid, it's this dense. And remember, a fluid is moving, it's flowing like a river. Imagine a river. So what we do is imagine a river flowing over just white paper, like a white background. And there's actually like graph paper with grids and coordinates. And the graph paper stays fixed and the water flows over it. Okay, that's the Eulerian description. And then sometimes we want to figure out other physical quantities. So we go into what's known as the Lagrangian description. And in the Lagrangian description, sorry, my camera keeps moving by itself. In the Lagrangian description, you are essentially in a boat moving along with the fluid. And in that case, these are not the coordinates. The coordinates are these. It's kind of in physics what people call like lab coordinates versus like center of mass coordinates. Basically, the coordinate system is it's almost as if you stay fixed in the boat and the water's moving beneath you. But in reality, yes, you are moving with the water. So those are like the two kind of viewpoints that we can use. So with that in mind, that's kind of the stage on which we're going to let these equations come out and entertain you. But the equations are going to be speaking in terms of those pictures. So yeah. Fluids and streamlines. Yeah. So remember the path line. Remember I just talked about the boat and traveling along with the boat. That's what this is. If I just sit in a boat and move over time, this is going to be my trajectory. And this is an interesting statement too. If I have this X and Y, and I specify at every point in space what your velocity is going to be, it uniquely determines these kinds of trajectories given a starting point. So that's essentially what the path line's saying, and that allows us to construct these path lines such that you can look at this graph and kind of get a good idea of what the fluid is doing and what it really means for stuff that's interacting. On the other hand, streamlines are just kind of tangents to the actual velocity distributed over space. So time is frozen here. Time is not moving. Delta time, 0, no time change. Time is frozen, and this is just at any point in time the velocity distribution of the water. So like in the field we just call it space and time distributions, but I guess they call it pathlines and streamlines here. That's just the example we went over. A material time derivative. Yeah. So this is just some general field he's saying, but you can set it to something concretely like momentum to make it a little easier to follow. But basically all it's saying is that the actual values of the field can change in time. So like we have the X and Y, and we have some point, and we have those fields we were talking about, U and rho. And he's saying just as time goes on, those fields will change for every single point. That's all that means. And then we have this, which is essentially saying that, reminding us that we're actually dealing with these little parcels of water, theoretically, and stuff can go in and out of them. So like pieces of water can leave, and pieces of water can come into it. And essentially, this is the rate of change with time, and this is how much the field changes over space. So you have essentially this thing flowing out, and if I'm here in the field, and then there's another point here in the field, and I go from here to here, how much is the field value going to change? So like if I'm sitting in a boat and I move a little bit over here, how different is the field? That is what this is saying. This is saying, how does it change in time? Combined, they're essentially telling you, if I do move here, how much momentum or field or whatever am I losing? Remember, that's called the effective term. We already talked about that. All right, conservation of mass. Remember, I said conservation laws are going to be kind of king here. This is the first one we got. This is a ubiquitous pattern in physics. It's called a local conservation law. So essentially what it's saying, and I think I said this last time, is that if you have a box and you have some stuff in the box, the amount by which some quantity calculated on the stuff in the box changes in time is equal to the amount of that stuff actually leaving that part of that box. And on its way out, it has to touch every single other box adjacent to it. So this is the idea that if we have some stuff in a box, right? This will be better drawing. So we have some stuff in a box, and let's say it's energy, and we want to conserve energy. Now, we can conserve energy if this disappears, this energy, and it pops up somewhere else in space magically or just instantly. That would technically conserve energy, but it won't locally conserve energy, and it's just not good enough for us in a physical theory. If you know any special relativity, in different viewpoints, like if you're going at different speeds in special relativity, this energy will disappear and appear at different rates. So like it's actually really, really bad if we don't have local conservation. That's why we force it. Because with special relativity, you can essentially just totally game conservation and technically respect it, but really not respect it and really fuck up with nature. It would be madness, basically. So that's why we require local conservation. And that kind of dovetails with this concept of a field, which is that if something moves from A to B, it has to touch every single point in between. That's local conservation. So this is saying the stuff in the box gets less or more with time. Okay. So if I have a box and I'm measuring the temperature in that box or some other like proxy of energy that changes, then that means that some energy flowed out of the box and touched every neighbor on its way out of the box. Got it? Okay. That's really all it's saying. And this is a statement of local conservation. And this is zero here because there's no external forcing or energy being added to the system. In this form, it is just a conservation law. And specifically, this is density. So it's conservation of mass. But you could change this quantity here to be electric charge. You could change it to be energy. Whatever the form is, it's always the same form for local conservation. This is just adding it up and integrating it, blah, blah, blah. Yeah, so this is vector calculus. And the old joke goes like, you learn vector calculus much better depending on how well your teacher can draw. So like if your teacher can't really draw, you're not going to learn vector calculus. Because something like this, remember, momentum is just mass times velocity. In this case, we're doing with density times velocity. Okay, it's basically the same thing as this. It's just local. And this little ds here, if you imagine like a curved surface or some sort of theoretical surface we draw in the water, ds is like a very little patch. It starts as what's known as delta s, and then we shrink it and shrink it and shrink it until it's delta s in the limit of infinite shrinking and zooming. If you think about looking out at the planet right now, look at the Earth, it looks pretty flat, right? If you fly up real high in an airplane, it looks a little more curved. So that's real. The Earth is actually curved. Sorry for you flat Earth conspiracy theorists out there, but it is. Now imagine looking at this surface from high up in an airplane and then going down. And the more farther you go down in the airplane, the flatter and flatter the surface starts to look. That's kind of zooming in and making this patch smaller and smaller and smaller. That is the process of taking this little delta s. And as you go into an infinite limit, it becomes this ds here. So ds is a tiny little patch on a surface of interest in water. So like we want a bounded surface to bound a finite volume of water. And we're going to take a little patch and we're going to add all those patches up. That's what the integral does. It's like an elongated S. It's like what S looks like in French, but it's just a fancy sum. It's a sum of these infinitely little things. And this is the amount of momentum that's escaping out of or going into whatever the flux is with that little patch. That's what this is. So that's what we're adding up. So see, depending on how good my pictures were, you now understand vector calculus very well or not so well. That's just the nature of vector calculus. It's very visual. Same. So he's basically just saying that we're going to call this. I'm actually not quite sure what he's saying there. Oh yeah, the material derivative thing. He's just basically calling this whole thing that. Okay, good. Incompressible fluids. So this is what I talked about before. A fluid that can't really. Sorry, I'm just gonna get some more and I'll be right back. All right, incompressible fluids. Essentially, a compressible fluid would be something like something that has elasticity. So essentially, if you have like some fluid and you can kind of compress it inwards like that, right? You can kind of push it in this region, and this region would like get a little more dense, and then the region can get a little bigger, but there's the same amount of molecules. That would be compressible. But we're saying that that can't be the case, and mathematically, that's represented by this divergence thingy here. And divergence is essentially, if you imagine like a spring of water like flowing out, that's positive divergence. And if you imagine water going down the drain, that's negative divergence. But this is not a divergence of water, it is a divergence of a velocity field. So essentially what it's saying is that if I have a little velocity here and the velocity gets bigger and bigger, this is happening, in a complete circle, that would be positive divergence. And they're saying that that is not allowed. Because were that allowed, think about a fluid, and then think about the center of the fluid right here. And the fluid is flowing very slow here. It's flowing really fast there. So if it's flowing really slow here and really fast here, there's going to be a strain, right? And that strain in a compressible fluid would actually make the region a little bigger and be a little bit less dense. They're saying that that's not allowed. And that's going to lead to a consequence later called Bernoulli's law. But the essential requirement is that we don't want a stretching of velocity to kind of be changing the fluid and compressing it. Now, the reason that it's not just saying in one line it can't get bigger, but it's requiring this circular kind of thing, is because there's a loophole here. You can actually stretch in one dimension and shrink in the other dimension and still respect this. So if you think about water, I can kind of have velocity getting bigger in one direction and pulling the water in one direction, but it's actually shrinking in the other direction, and that still respects divergence. That's why we're very careful in saying divergence and not just this. That's why math is so specific and rigorous, is because it respects that condition. So yes, it leads to what I just said, which is that the density is also not changing in that way. That's what rho is there. Yeah, so it's basically just saying that what we're forbidding is actually how sound happens. And because we do this thing in the velocity field, we can write it in this way. And again, if you know some physics, the magnetic field actually has this same requirement. That is, it is known as the magnetic monopole restriction. The divergence of the magnetic field has to be zero. It basically means there are no magnetic charges the way that there are electric charges. It's actually literally the same math, but very different physical content. This is not super interesting to me now. It'll come up later, but it's essentially this idea that if divergence is so if this is zero for some fields, then we can write some potential like gravity. It's conservative. It goes the other way too with if the divergence is zero, we can also write a potential, but it's going to be a vector potential. But in this case, it so happens to work out that we can write it as a scalar potential as well. But if you know anything about magnetism, this is literally the same math. So yeah, you can just write it as a vector potential. Well, there's an example that uses this later that's interesting. This is basically just saying we can put this in a more compact form. So like think about it as the magnetic potential if you know any magnetism. If not, then essentially this requirement, which is what this stuff I just talked about up here, that constrains the equation such that normally you'd have like this field in 3 dimensions, and at each point it can have an x and a y and a z. This eliminates some of those, and it kind of couples different dimensions such that this has to be respected. And because of that, we can write it in a more compact form. That's really all it's saying. And this is that more compact form. So I can literally just write this vector potential, and then if I'm curious about what the actual components of the field are, I just take that, and they actually relate the 2 coordinates, the I and j coordinates, in a certain way such that I can write it in that more compact form. And that's just the same thing in polar coordinates, which makes it a little more intuitive. Okay, in viscid flows. So we talked about viscosity a little last time. Remember, viscosity is a second moment. V, or it is G. Plus some constants here is viscosity. That's how we write viscosity. So the idea is if I have a molecule here, and I have a molecule here at a different point in space, how is the y component of the velocity of this guy correlated with the x component of the velocity of this guy? And what viscosity really is you have different sheets of fluid, and if this fluid's moving here and that fluid's moving there, they kind of have this drag force on each other. It's the analog of friction in fluid mechanics. So what we're going to assume within viscid flows is that there isn't any viscosity, right? If you imagine honey, it's like really gooey and viscous. It has high viscosity. Take it, the viscosity lower and lower, it becomes water. Even water has some viscosity. So if you keep going even lower and lower, you get this theoretical fluid that doesn't really exist, that has 0 viscosity. So that's what we're imagining in our head. And we're going to see what kind of physics we can get out of that before we have to make it more realistic. That's the program in theoretical physics. We make it as simple as possible, get all the physics we can out of it, and to the degree that it's not reflecting real physics, we know that we're being too idealized, and we have to add more bells, and we have to add more constraints to it. We have to maybe say, okay, yeah, there is viscosity in real life, so maybe we'll make a simpler version of viscosity and see if we get in our theories, this real phenomenon that we see in real water. But we're going to start simpler and assume there's no viscosity at all. And we're going to assume mass conservation, and we're going to assume incompressibility. And out of that, we're going to get this thing, which is basically the Newton's second law for fluid. And this is a proof of why we get it. So essentially, remember that the plane and the little patch and the zooming in, this is an even better illustration of that. So we have, where's my proof? There it is. Okay, so yes, there's delta x. Remember I told you about delta x? So delta x is basically the Earth is curved, but you take a little tiny patch, and as you make the patch smaller, the Earth looks less and less curved. It looks more and more flat and linear. And this little delta thingy here is making the patch small enough that saying that the Earth is really flat is a decent enough approximation. So if you zoom in far enough, the Earth does look flat. The farther you zoom, the lower the error. This is saying that we're zooming in far enough that the error is tolerably low. So that's what this is here. And then we're saying through that little patch, there's a certain amount of momentum flowing. This. And we're going to multiply it by time, a little tiny increment of time, delta time. So in a certain amount of time, there's a certain amount of momentum that is flowing through this little tiny patch. And it creates this kind of thing over because of the time. And if we add them all up, that's what this integral means. You essentially get the total amount of stuff that's flowing out. So basically, if I took like the whole object, there's like a lot of different momenta at different points in space that are flowing out along a very complicated curved surface, and the math is a nightmare. So what we do is we concentrate only on a little tiny part that is flat, make the math really easy, and then there's really only one momentum value at that point. So it's basically just multiplication, the amount of momentum times the tiny little area, and then we add them all up. That's integration basically. And we use the divergence theorem to turn that into this volume integral. Don't worry about the math there, but this is the important part. That's what we get out of it, which this is the Newton's second law for an inviscid, incompressible fluid. It has a name, I believe it's the Euler equation. Let's break down what it actually means. Okay, so we see this volume integral over the density times the velocity. The i's are here is because velocity has different components in different directions. There's x velocity, there's y velocity, and there's z velocity. The I goes over those dimensions. And we're integrating it over a volume. Plus, this is the amount that flows out. This is how it changes in time. It's kind of like ma, F equals ma. This is new. In normal mechanics, F equals ma is the end of the story. But in fluid mechanics, remember, stuff can enter and leave this parcel of water. So we need this term as well. And what this is saying is that we're taking the how this quantity, the velocity, changes along a certain spatial dimension. So, for example, this J and this is called Einstein's summation convention. This J and this J add up. So what we're going to do is we're going to take how this thing, which is just v squared kind of, changes with respect to the x dimension, and then we're going to do the y dimension and then the z dimension, and we're just going to add up all over those. So if you remember the multiplication rule, in it's like how you take a derivative rule. This ui uj would actually look like this. You take the derivative of ui, right, with respect to uj, and that whole thing would just be multiplied by uj, right? Remember remember from first year calculus, you have these two functions multiplied by each other, v and u, and the rule is that you just kind of take dv dx times u, and then you take du dx times v. That's just what we're doing here. It's no more complicated than that, actually. You're taking how ui changes with uj and multiplying it by uj, and then you're taking how uj changes with uj, and then you're multiplying that by ui. But remember what we assumed: incompressibility. Yes, the divergence is zero. So that means that how uj changes with uj, add over xyz must be 0. So good, that's going to save us a little bit of work. And it's why only the second term survives there. Because if ui, uj, that survives. But when we're taking how uj changes with j and adding that up, that equals 0. So this goes out and only this first term survives. And that's what this is down here. Just that. And we repackage it into a nice little delta, little tensor here. And it looks so much prettier now. So yes, this is the final form of the equation. And I got a little overzealous in my drawings here, so I'm just going to kind of clean this up. You can this is a very important equation, so I want you to see it without my silly drawings in the way. Yes. So what this is saying is that the change in momentum is equal to the force exerted. F equals ma, but in fluid mechanics. Beautiful. So now we're going to complicate it a little further, and we're going to add a concept of pressure. Still approximation, still an idealization, but we're going to consider pressure now. We're going to add in a new bell and whistle in our physical theory to make it more realistic. Pressure, for those of you who don't know, is just the force over an area. So if I have like an area of a tire or something, the amount of force that's being subjected to that area and only that area is the pressure. Surface, it's just this thing. What we do is we say in this little area of, say, a tire, there's this much air pushing on it, and then we add it up over every single little region. And then we get the pressure that's on that tire, the PSI, when you do your little tire gauge. That's what it is. And the equation we saw before, this is just a repackaging of this entire thing. So this is this equation again, but we're considering pressure as well. That's all. And you can read through these parts of the notes if you're interested, but basically, if we assume some simple force like gravity, which does act on most fluids, you can get Archimedes' law out of these assumptions that we just made, which is that if you put something in fluid, does it sink? Does it not sink? This is kind of an aside about the equations of state. It's just saying that pressure, volume, and temperature are all kind of functions of each other and constrained to each other in a certain way. This is back to that. So yeah, I think he gets Archimedes' law later. Yeah, Archimedes, there it is. Right, exactly. This is called the Euler equation, and it's just basically assuming momentum is conserved. That's all. And F equals ma also is a statement of this. It's essentially saying that if there's not an external force acting on something, then momentum is conserved. This is the same thing, but for fluid mechanics. So this is the final equation. We recognize it. This is the change in momentum with time. This is how much momentum flows in and out. And this is counting for the pressure. Pressure is isotropic. It's the same in all directions. And it's basically either pushing in or out. So we can just kind of say it like this. Easy. This is a momentum current. It's a conserved current. Remember, we talked about conservation before. This is a tensor. This is a delta. What it basically means is that this is a sum over I and j. So essentially, it's going to be like a lot of components. One is going to be like the density times the velocity in the x direction times the velocity in the y direction. And because these are not the same, this is 0, so you don't get a pressure component. But every single time the I and j are the same, like for example, xx, then you do in fact get a pressure component in the xx direction. That's what this says. There's like 9 of them. It's a tensor. It's a whole mess, but it's a current and it's conserved. So this Archimedes principle, right? So this what's cool is that if you Archimedes just kind of discovered this empirically or semi-empirically, but if you assume what we just assumed and you kind of work through it, Archimedes principle actually kind of pops out of it. Oh shit, I forgot to give you my puzzle, but I think we're almost at Bernoulli's principle, so maybe I can just do it now. Yeah, awesome, Bernoulli's principle. So energy conservation and Bernoulli's principle. So what I'm going to do is give you this puzzle at the end of the notes, and you can think about it for the next time. Okay, so remember, we just did momentum conservation, but energy is conserved too. So we want to do the version of energy conservation for fluid mechanics and get some more equations. So essentially, this is just a standard vector calculus identity. You can look up the proof if you're interested, but it allows us to massage the equation we had before into this form. And then we have what we had before, this. This is actually just literally vector calculus. Like there's no real tricks. You're literally just applying this identity. So I have nothing more to add to it. PU, okay, UF. Yeah, so he's just kind of basically applying that identity. And we're making one more assumption, which is that the forces acting on the fluid are all conservative forces. And we're using gravity as the example. And this is the key quantity here, which allows us Bernoulli's principle. It's saying that the kinetic energy plus the pressure plus the conservative forces do not change. So yes, exactly. Now, this allows us to do some real physics now. We can start deducing some interesting stuff. So this has to be the case. As a fluid flows through a pipe, if we narrow the pipe, we can now predictably say, because the area is going, we need to say UA is conserved. So if this goes down the kinetic energy, if the fluid slows down, then the pressure needs to go up, because this needs to not change. That's the beauty of conserved quantities and why we like them so much in physics. They allow us to do stuff like that. So you can go through this in the notes. It's a good exercise left to the reader. But this is very cool, the ping pong ball thing he talks about. So if you have like a jet of air that's flowing, and you have like a ping pong ball in the center, and the air kind of will probably go around like that. It'll go around like that. It'll kind of like that, right? Imagine you're having some fun with a wind tunnel. And why, if you actually do this in real life, the ping pong ball is going to stay in the center here. The question is, why does it stay in the center? So imagine that the ping pong ball moves a little bit over to there. So now the ping pong ball is here, and now the air is over here like that. Yeah. Okay. So if it does do that, notice that the ping pong ball is exerting drag on the airflow here. So this whole airflow in this whole region is moving slower than it is moving in this region, right? That sounds good. Okay. So if we move it over to here, now in fact, this air is moving slower than this, and this air is moving really, really fast. So because of Bernoulli's principle, when air is moving faster, the pressure has to go down, right? It's moving faster, the pressure has to go down. Now, if the pressure goes down in this region, things want to flow to a region of less pressure. If you think about it rigorously, it's because the total amount of force acting on the thing is lower here, then it's higher here, then it's going to be pushed this way. This is a lot of how weather works. If you look at the barometric pressure, when it's low, that means pretty much a storm is coming. Hurricanes move towards lower pressure areas. Fronts move towards lower pressure areas. This ping pong ball is going to move towards the lower pressure area back into the center, right? So that's really cool. Just from those kind of arguments, we can just say that this is going to be a stable equilibrium, even though, like he says, there's vorticity and there's turbulence and there's a lot of complicated things in fluids that mean we can't just sit as theorists and we need to use a wind tunnel ultimately at the end of the day, but it provides that answer. Now, here's where I want to leave the lecture off on Bernoulli's principle as it's classically applied to the idea of why planes can fly. So he brings up a good objection, but I have another objection to this idea. So it's basically saying we design an aerofoil, like a wing, such that the air has to flow faster up here, then it flows down there and slower down there. And because of that, the pressure is higher here and lower here, and that makes the plane want to lift. It generates lift. But here's my question. If we design an aerofoil geometrically that way, think about the plane, flipping over or doing a barrel roll. Planes can fly upside down, right? If you've ever seen a plane tilt upside down, it doesn't just crash. It's still generating lift because planes can just fly no matter what. So if that's true, then what the hell's going on here, right? Because now the top is at the bottom and the bottom is at the top. So why is the plane still flying? That's what I want you to think about for our next lecture, okay? Consider that puzzle. Why can planes fly upside down? Because Bernoulli's law is roughly right. That is roughly why planes do generate lift. But there's a wrinkle that you guys need to think about that allows planes to fly right side up or right side down, or upside down, and still generate lift. So, a fun little brain teaser for you, and I will see you